Hello everyone, welcome to the Section 2 examples for the Mathematical Proofs lecture series. So before we begin these problems, I want to explain a new writing format that will be used for examples that are without proofs, and I wish I would have started using this format in the previous section, as this is kind of a format that you would normally see inside textbooks and that a lot of mathematicians use to write to write out their solutions to examples or to problems. So they often include a title, which is the solution, sometimes in all caps, sometimes all lowercase, and sometimes underlined. And they also include a symbol, which is often a diamond symbol, to identify the conclusion of the solution. So I'm going to be using those for these examples and for any non-proof based examples going forward. So just wanted to mention that real quick to explain some of this new writing format that you may not have seen in the previous section. All right, so let's look at the first problem. We are given the open sentence P of x, where 8 of x is greater than 2x plus 1 over the domain of integers. And we are asked to determine the values for which the open sentence is true and the values for which it is false. Well, let's start out by determining which values are true and false by just rewriting this inequality. So you can subtract 2x, 6x is less than 1, and that gives you 6x is greater than 1, and then x is greater than 1 over 6. So the values for which this is true, we can just write this in the form of a set where x is an integer, rational number, because 1 over 6 is not an integer. So those are the values for which the open sentence is true, and then for the values where it is false, be where it's less than or equal to 1 over 6, because our inequality is strictly greater than. So this is all there is to the first problem. And sometimes in the notes we'll do this, it'll automatically think I'm drawing a diamond. It's probably not going to happen all the time, but it is a little bit nicer because sometimes my hand-drawn diamond symbols aren't the best. All right. So for the second problem, we're asked to state the negation of the following statements. The shape has more than 8 sides, and everyone loves math. Well, if you remember for negations, they have the opposite truth value of the statement that they come from. So we just need to write something that's surprising, something that's different from the original statement. So for the first one, we can say the shape has less than 8 sides. And then for the second one, we can say not everyone loves math. And I like math and think that it's fun, but this negation has a more likely truth value than its original statement because it's not everyone's cup of tea, but these are the negations of these statements. Just trying to erase those extra streak marks over there on that diamond. It's not a perfect diamond, but we'll use that. There we go. All right. Problem 3. we are given two sets, A with elements 1 and 4 and B with elements 2 and 5, and we are given the two statements P, the Cartesian product of A and B, and Q, the Cartesian product of A and A. So we are asked to determine the disjunction of P and Q and the conjunction of P and Q. So the disjunction and conjunction of the statements. So I think the first step we need to take is we need to determine the Cartesian products. So let's do that first. These are the ordered pairs for the Cartesian product. When you multiply the two sets together, then we'll find the other Cartesian product. And it's just the set A multiplied by itself. And that gives us this new set. All right, so P disjunction Q is going to be equal to the union of the two Cartesian products. So that's going to be equal to all the ordered pairs in all the sets. And I don't believe any of them repeat, so we'll have to write every single one of them out. All right, and then for B, P conjunction Q, it's going to be where the Cartesian products intersect. However, they don't share any elements in common, so it is the empty set. Here we go. It's a pretty diamond symbol. All right, that's problem 3. All right, problem 4. We are given the sets S with elements 7, 8, 9, A with an element of 8, and B with an element of the set 7, 8, and another element with the set 9, with the set with the element 9. And we are given these two statements, P, A is a partition of S, and Q, B is a partition of S. And we need to determine the truth value of the following statements. The first one being P implies Q, the second one being P conjunction Q implies P, and the third one being not Q implies not P. So for this solution, the best way to determine the truth value is to make a truth table. And I already formatted one out here just to save time, so you wouldn't have to see me draw it, and also to help me avoid making a mistake with the columns. So let's fill out this truth table, and then we can look at determining the truth value of the statements. All right, So P conjunction Q is only true when both P and Q are true. P implies Q is only false when P is Q and true is false. Then P conjunction Q implies P, that is only true, or is only false when P conjunction Q is true and P is false. And then not Q implies not P. Let's see. They are both false, so they're true. And yeah, this will be false because not Q is true and not P is false. And then, yeah, not P is true. Not P is true. And let me, P conjunction Q implies P. Yep. All right. This truth table is correct. So now, let's determine the truth value of the following statements. Okay, well first, we need to look at these two statements here. A is a partition of S. This is false. Because if you remember, a partition is a set that has elements, that has all the elements that are inside sets that are in a new set, or at least it's somewhere around that definition. Sorry, that may not have been the best way to word it, but you can look up, you can go back to section 1 notes and figure out what a partition is. You remember the partition pie example where the pie was cut into pieces and all the elements were inside each little piece, but yeah, that's basically what a partition is. So A is not a partition, or P, well, A is not a partition of S, which makes P false, but B does match this definition. It is a partition of S, which makes it true. So we need to look here on the truth table, and we are at where P is false and Q is true. So we are here in this third column. So P implies Q at this specific statement has a truth value that's true. P conjunction Q implies P has a value that's false. And not Q implies not P has a value that's true. So I'm actually going to write it like this, just to say writing A is true, B is false, C is true. And that's problem 4. Alrighty, for problem 5, we are given these open sentences, P of x, where x divided by 2 equals 5, and Q of x, 3x plus 6 equals 12, over the domain of integers. And we need to state the following 4 statements and words and determine the values for which they are true. Okay, let's first start this problem off by rewriting these open sentences. So we can rewrite that as x equals 10, because we can just distribute that 2 or multiply the 2 to the other side of the equation. Then for Q of x, we can write it as, so we subtract 6, we get 3x equals 12, which gives us, that's not a good arrow, I'm trying to make a little better one, x equals 4. So let's look at part A. So we have not QX disjunction PX. So not px, that's going, or not qx, that's going to be when x does not equal 4, which is going to be separated from x equals 10. So let's write this out in words. Qx is not equal, sorry, I made a mistake here. It's supposed to be 2. 2, and px is equal to 10. And this is true when x is 10. And you can construct a truth table if you want to look at the truth values, but we're looking at these logically just to save writing. So the second statement, you can write it out in words. Px equals 10 implies Qx equals 2. And this is true for, we can write this as a set where x is an integer, and the only condition is that x cannot equal 10. So it's basically every integer that's not 10. All right. For the third statement, px equals 10 if and only if Qx equals 2. Well, this is true for, we'll write it again as a set, because there is basically infinitely any truth values for this. It's true for every integer except for the solution, except for where x equals 10, or except x cannot equal 10 and x cannot equal 2. The solutions of the true values for the open sentences. All right, for the fourth part, let's scroll back up here. We're writing out the biconditional of not px and not p and not px and not qx. And just for clarity, B was about px implies qx, and the C is the biconditional of px and qx. So px does not equal 10 if and only if Qx does not equal 2. And this is true for x equals 2 and x equals 10. And that is problem 5. Okay, don't know what happened there, but all right, so let's look at problem 6. So we are given the statements P, 23 is a prime number, and Q, 7 is even. And we are asked to determine if the compound statement, if 7 is not even, then 23 is a prime number, or 7 is not even, and determine if that is a tautology. So let's break this down. Let's break down the words and figure out what's being stated here. Well, Q is 7 is even, so 7 is not even. That's not Q. 7 is not even. And then we have, then 23 is a prime number, or 7 is not even. Well, remember the word or implies a disjunction. And also, we have the words if and then. If you remember going back to the lectures, that states an implication. So, let's write down the second statement. "23 is a prime number." 23 is a prime number, or 7 is not even. Okay, these are the two logical these are the two statements that are simplified without all the words. So what we need to do is we need to construct a truth table to determine the truth value of this statement and if it's a tautology. Now, there's not a lot of columns for this one, so I'll just write it out. And we have not Q implies P or not Q. Alright, so let's construct this truth table. So we have true, true, false, false, true, false, true, false. Then not Q is the opposite truth value. Then we have P or not Q. Well, that's only false when both P and not Q are false. And then let's look at the implication that's being made here. So remember, an implication is only false when the statement on the left is true and the one on the right is false. So doesn't look like not Q implies P not Q. That's not happening. So looks like this is a tautology because it's true for every possible combination of truth values for its statements. So let's write it out in words. Therefore, if 7 is not even, then 23 is a prime number and this is a disjunction, say or 7 is not even is a tautology. And that is the conclusion of this example. Didn't make a diamond symbol for me that time, but that's fine. All right. Problem 7. Problem 7 gives us two statements, P and Q, and it asks, is the biconditional of Q and P implies not P implies Q, a contradiction, and it wants us to verify that not P implies Q conjunction P disjunction Q is logically equivalent to not P implies Q or the disjunction of P or Q. So this is going to be a big truth table because we need to figure out the truth value of these statements and recall or remember a contradiction is a statement that has a false truth value for all of its possible statements or possible combination of truth values from its statements. So for part A, we'll just be looking at when we fill out the truth values for this statement, if all of them are false, if one of them isn't, then it's not a contradiction. And then for part B, where if you recall from De Morgan's law, this is an example of De Morgan's law, and we're just going to use logical equivalence. If the two statements have the same truth values, then they are logically equivalent and the statement is verified. So let's start by filling out this truth table. Of course, I've already filled this out and I'm just copying it off of notes. But I'll be glancing over time to make sure there's not any mistake I might have made while filling this out. But hopefully there's not, because there's a lot to look at here. But these are just all the statements broken down. And their respective truth values. Looks like a line has gone missing here. My mistake when drawing this. Alright, not P. True, false, false. And we have true, false, true, false. Then for the biconditional, we have true, false, false. True. And then this is a statement we're wanting to determine whether it's a contradiction or not. Well, let's take a look here. For the first one, that is false, but it is not false all the time, so therefore it is not a contradiction. And we'll write that down here in a minute. But for part B, where we're having to verify these two statements, we'll put down the truth values here. These are logically equivalent because they contain the same truth values. So what we can determine from this is that A is biconditional if Q or P implies not P implies Q is not a contradiction. And for part B, see truth table. All right. Problem 7 is done. Had to make a quick cut in the video, but when I did make a quick cut in the video, I reworded problem 8 to make a little more sense for what the problem is asking for. So let's take a look at problem 8 now. So we are given S is a set with elements 2 and 4, and we're given two open sentences. P of x is x squared minus 6/8 plus 8 equals 0, and Q of x, where x is an element of S. And these are open sentences with the domain of integers. So we are asked to rewrite the following statement using quantifiers, and the statement we're given is for every integer x, x is an element of S. And then we're also asked to identify if Qx is a characterization of Px. Well, part A is pretty straightforward, so let's start with that part first. We're asked for, the statement we're given is for every integer x, so we will use the universal quantifier. So for every x that's an integer, then x is an element of S, well, that's just Qx put in words, so we can just say Qx. And that's a simplified, rewritten statement using quantifiers. So to determine if Qx is a characterization of Px, recall that for it to be characterized for every x that's over the domain, the biconditional between the two open sentences, or there needs to be a biconditional between the two open sentences. So let's take a look at Px. So Px, we have this quadratic equation, and you can either use the quadratic formula, or if you're able to notice, you can FOIL it out. And that gives us x equals 4 and x equals 2. Well, that's the same as Q of x, where it's an element of S, and S has the elements of 4 and 2. So we don't have to write out a truth table, we can just logically deduce this. So we can say, yes, Qx is a characterization of Px because for all x, oh, that's an integer, here's a biconditional between Px and Qx. So Px if and only if Q of x. These are the only satisfying integers for the equation of Px. And that is it for the examples for section 2. Alright, hey guys, thank you so much for watching. Hope you enjoyed this video on section 2, and we're now done with the fundamentals of mathematical proofs. So in the next section, we will start looking at proof techniques.